Now, after all this long introduction, I think this will clarify things and will enable us to go back to the group, to the specific lattice we studied, which really represents an algebraic group, which is neither SL2 nor PGL2, but it's kind of similar to them. This is the so-called a form of SL2. I don't want to give the precise definition, but there are more algebraic groups, and this algebraic group that we are studying is, if you look at it over the complex number, this is the same as PGL2. But over a ring, it behaves somewhat differently. So let me recall now back to our arithmetic group. So let me recall what we did. We look at the quaternion algebra H over some ring R ring. So this is x0 plus x1i plus x2j plus x3k, where the xi are in the ring R, and as usual, I square equal j square equal k square equal minus 1, ij equal k equal minus ji. This is the quaternion algebra. Now we specifically looked our algebraic group, if you want, as an algebraic group, is taking h, g of something, is the g of the something, the h of the something, star, the invertible element there. This is an algebraic group because this is really something which you can express by polynomials, whether something is invertible or not, and dividing by the center of this stuff. For example, if you do it over the complex number, indeed, g of the complex number, so we know that h of the complex number is the 2 by 2 matrix, divided by the center. So this is, and the invertible element is like GL2C divided by the center. So this is PGL2C. So you see that eventually, as an algebraic closed field over the algebraic closed field over the complex number, it really behaves like PGL2. So it won't be so surprising that it behaves like PGL2. Z also along the way, and now we want to study it more carefully. Okay, now let me recall that we looked at G of Z1 over P. You remember, this was really what we studied. We look at Z1 over P. This sits inside G of R cross G of QP, P odd, and we even assume that P is congruent to 1 mod 4. Now this is compact, and this is isomorphic. We saw that by the same argument basically, because the quaternion algebra splits over QP. If P is congruent to 1 mod 4, then you have square root of minus 1 inside the field, and then if minus 1 is a square inside the field, then the quaternion algebra over that field is isomorphic to the 2 by 2 matrices. So this is PGL2 of QP. And that's what gave us the lattice gamma. Now the projection, this gave us gamma as a lattice in PGL2 QP. But this one contains also some torsion. You remember we saw the torsion, these elements, the invertible element. We really concentrated on a subgroup of finite index lambda, which was generated by S. What was S? S was a set of alpha 1. Well, if we want even to be more precise, alpha 1 up to alpha S alpha 1 bar up to alpha s bar, where s is exactly p plus 1 over 2. What we saw, if you remember, that the alpha, that s was really all the elements alpha in hz. We really took integral quaternion of norm p. We can think of them as elements of our group, because if you remember, elements of norm p, so let's say the norm of alpha is p, and if you write alpha as x0 plus x1i, etc., then x0 is greater than 0 and odd. Okay, you remember now? We took this specific p plus 1 element satisfying this property, and we show that there are p plus 1 elements like that because of Jacobi theorem. Each one of them, you consider it as an element, this is an integral quaternion, but it really sits also in z1 over, in h over z1 over p. And the norm of it is p. P, here is the trick. P is not an invertible element in the integers, but it is an invertible element in the ring z1 over p. And therefore, such alpha is invertible element in h of z1, in h of z1 over p. It's invertible. And what's the inverse of such an alpha? The inverse of such an alpha, alpha to the minus 1, is really equal to alpha bar divided by the norm, divided by p, which means that alpha times alpha bar is equal to p. Now, p as an element of the quaternion algebra is in the center. So if we divide by the center, so p for us is identity, and therefore alpha bar, we can consider alpha bar as the inverse of alpha. And that's exactly alpha 1, they appear in pairs, alpha 1, alpha 1 bar, alpha 2 bar, etc. So these are elements, we can think of them as elements of gamma, and we saw that if you take the standard lattice, these p plus 1 elements take you exactly to the p plus 1 neighbors of the standard vertex, and we deduce from that this is a free group on these p plus 1 generators, right? All this we did last time. Well, or to be more precise, is a free group on half of them, because they appear them, and it's a free group of rank what's called p plus 1 over 2. And these p plus 1 generators are exactly a set of elements and their inverses. Okay, you are all with me? Now, and then we saw that the Cayley graph, so the Cayley graph of lambda with respect to s is kind of in one-to-one correspondence with the tree which is the building of dimension 2 over the field QP. So we have kind of a beautiful way to think about the building associated with PGL2QP as a Cayley graph of that group lambda. And we wanted now to look at the groups, at the congruent subgroup. So this lambda, okay, this we did not quite prove all the details, and I think I'll skip it, because anyway, you can, if you want to Q large enough. So really, the story is that lambda is exactly gamma 2, the congruent subgroup mod 2. If I look at in the notation that I talked today about gamma of the ideal 2. And now, if Q is, say, a prime, doesn't matter really, we can look at gamma, better to say gamma 2q, which I will call it also gamma lambda 2q sometime, or q, whatever you prefer, inside gamma 2. And because of the strong approximation, okay, now what we want? We want to study the building P2QP divided by these groups lambda 2Q, lambda 2Q. Why? Did I tell you that already? As a black box that these are Ramanujan graphs? I told you that or not? Right, the theorem is if you take congruent subgroups, these are Ramanujan, right? These are P plus 1. We know that these are P plus 1 regular Ramanujan graphs. So they are, and now this semester I'm not going to explain at all why. You will get it, maybe we'll come back to that in the second semester. But fact, if you take the building, you take an arithmetic group, now today you understand what is even more general arithmetic group, not just the one I built. And you take a congruent subgroup, the building modulo congruent subgroup give you our Ramanujan graphs. What?
Principal congruent subgroup.
No, any congruence.
You can get a bound for any congruence?
No, because any that's
You
actually
can get tau, but you can get
No, it follows because you see, what is Ramanujan? All eigenvalues are in some interval. If you take, it's a small.
You reduce the
If it's true for principle, here the principle are nicer to start. But okay, so this is Ramanujan. But this is equal. This graph is equal to the Cayley graph of gamma. You see, I can identify these three with the Cayley graph of lambda with respect to S. So if I divide it, I can identify it with the quotient group with respect to S. Now this is already a big achievement, even if I don't know to compute anything here. This is a big achievement because I'm getting here not just abstract graphs, I'm getting here Cayley graphs, which a lot of symmetry. Cayley graphs are the most beautiful graphs. Right? So I'm getting Ramanujan graphs here, which are Cayley graphs. So the goal from now on, I can forget, in some sense I can forget the periodics, I can forget the buildings, and the goal is to compute what is this group and how these generators appear explicitly within this group. So this is our goal now. Okay. Now, I think I started to tell you. So let's see. This we had gamma over gamma 2q. Lambda is basically gamma 2 over gamma 2q, right? Is inside. Now this group is mapped to the group G of the ring Z1 over P divided by the ideal 2Q. I have to, there is something which little bit kind of nuisance which is going to bother us. Let me kill it so that we can really concentrate on what is important for us. Now this is mapped to G over Z1 over P divided by the ideal 2 times G of Z1 over P divided by the ideal Q. Right? This is just like the Chinese remainder theorem. if I take the ring Z or C1 over P, doesn't matter, modulo product of 2 points, I can really factor it. Now, I don't care about this group. Why? Because gamma 2, which is our lambda, which is gamma 2, goes here to the identity. On the other hand, by the strong approximation, it projected onto this Q. Now, let be a little bit careful about the onto. It projected, you see, okay, now I have to explain something. The argument I gave you before, okay, maybe let's say something. Assume, let's be careful, okay. Assume, for simplicity, this is true, there's also Q is congruent to 1 mod 4. So what is G of Z 1 over P divided by the ideal Q? This is really G of FQ, right? But what is G? What is the algebraic group G? This is the quaternion over the field Q, invertible element divided by the center. What is the quaternions over FQ? They split, right? -1, we have a -1 there. In fact, between you and me, the quaternion splits over every field, a finite field. But it doesn't matter. I mean, we can do it explicitly, and I really want to do it explicitly, for Q congruent to 1 mod 4. So this is the 2 by 2 matrices. I take the invertible element, so this is GL2. I divide it by the center, so this is really equal to PGL2 FQ. So I have a map now from lambda to PGL2 FQ. So this and lambda over lambda Q is in the kernel. And the story is exactly as the story I described before for GL2Z. And I don't want to get here to the little details. I just want to say that the image always contains, and the same proof, the image contains PSL2FQ, which, if you want, I gave you a full proof, which the same proof work here. At least I gave you a full proof, Q is large enough. Because also here the group is free. You remember I gave you a proof that if you have a free group which is mapped to PGL2Q, then it must be for infinitely many, at least contains PSL2. Because if it's not contain PSL2Q, it will be proper subgroup, and then this is impossible, remember, with this meta-abelian story. So the image at least contains PSL2 FQ, and so it's either PSL2Q or PGL2. Okay? But that's actually an important fact for us, an important point, whether this is onto or not. And I want to do this analysis now. And I want to check what's the story. What happens to the image of our group? Is it really PSL2 or PGL2? Okay. Now, what we know, let alpha be an element of S. And then let pi, if you want to be more, the map from lambda to PGL to Q. Right? We have such a map. Let's follow what happens to this alpha, where it goes. So let's do it in a very concrete way. Alpha is something like x0 plus x1i plus x2j plus x3k. And then I, first of all, this is as a quaternion with xi integers. And that's the way we start. This is a quaternion of norm P. And then I'm doing, it goes to the same alpha, blah, blah, but now xi are in fq. Simply mod q. Quaternion mod q, right? But then I'm doing a splitting. I take quaternion mod q and I make them to be matrices. The matrix is, you remember we saw when you split it, x0 plus x1 epsilon, x2 plus x3 epsilon, I think minus x2 plus x3 epsilon, and x0 minus x1 epsilon. You remember this is the splitting of the algebra when epsilon is the square root of minus 1 inside f cubed. This is the way to split the algebra, the quaternion algebra, to show that the quaternion algebra over the field fq is isomorphic to the 2 by 2 matrices. And so, and then, now this is an, okay, what happened? Here alpha, the norm of alpha, is equal p. Here the norm of alpha is also equal p, but I have to think about p mod q, right? That's really the meaning. And here we get that the determinant of alpha is equal p mod q. Okay? And now I'm going to PGL to FQ. Now, here we are coming to the crucial point. Is the image inside PSL2 or not? Now, I have here, so I call this also alpha. Let's call this phi of q. Now, phi q of alpha is inside PSL2q if and only if there exists some element z in the center. So z is a matrix z0, 0, z in fq star, such that alpha times z, the determinant of it, is equal to 1, right? Exactly as we did before. Before I checked it for the matrix minus 1, 0, 0, 1, you remember, to check whether the image of it is inside PSL2Q or not. To be, the image will be the image of PSL2 if and only if this matrix is congruent to SL2 modulo the center. Okay, so let's see, can we solve this? What determinant equal to 1? So this means that the determinant of alpha times z squared equal to 1. This means that the determinant of alpha is equal to 1 over z squared. Can we solve it? This is equal to p. And everything should be solved mod q. So when can we do it? If and only if p is a square mod q. That's exactly the so-called Legendre symbol. You know this Legendre symbol? Legendre symbol in number theory is it has some important properties, etc., but we are not really, what's called Gauss, how you say it? What?
Reciprocity.
The reciprocity. What? Quadratic reciprocity result, etc. But now we see that the image, now what is important to say here, that alpha was some element of norm P, right? Doesn't matter which one of them. If you have solution, you have solution for all of them. So either you have a solution or you don't have. So what we get, that the image of lambda in PGL2Q is equal to PSL2Q, everything is inside, if and only if P is quadratic residue mod Q. Namely, if and only if in the Legendre symbol notation, P over Q equal 1. And the image of lambda in PGL2Q will be PGL2Q, because we know that if it's not PSL, then it's everything, right? If and only if P is not quadratic residue mod Q. If and only if P over Q is equal to minus 1. But let me explain you that this is not a minor point. This is from the combinatorial point of view. It gives us a lot of information, because corollary, if P over Q is minus 1, first let's start with this case, then the Cayley graph of lambda over lambda Q, or lambda 2Q, whatever we want to call it, with respect to S, which is now we understand that this is the Cayley graph of PGL2Q with respect to the image of S, and we can really follow. By the way, we can solve this equation, we can follow, we can give explicit generators for this group, is a bipartite graph. The two sides, one side is PSL2 Q, and the coset and its coset is the other side. You see what we have? We have PSL2Q as a subgroup of index 2. And we have so we have this group and the complement of it, which is a coset. All the generators are outside PSL2. That's exactly what we proved here, that all the generators, not just one of them, because all of them are of determinant P, none of them is congruent to SL2 because there is no solution to this equation. All of them are outside, and they play kind of they go back and forth like ping pong from one side to another. Think about it. If you have a Cayley graph of a group G, the group G has a normal subgroup of index 2, and you take a Cayley graph so that all the generators are outside. So if you are on the side of the subgroup, all the generators take you outside. If you are outside and you multiply by one of the generators, it takes you back inside, right? Because the quotient is of order 2. This is clear, right? But I'm telling all this in details because I wanted to think about it. I don't want to write it down. That's a lemma. Take it as an exercise. Assume you have a Cayley graph, which is bipartite. Then it must be of this form. Namely, if you have a Cayley graph, you know that it's a Cayley graph, and you know that it's a bipartite, then there exists a normal subgroup of index 2 such that all the generators are taking you from one side to another. It's a very easy. Int for the proof. Take the side which contains the identity and prove that this is a subgroup. Prove that subgroup of index 2, and all the generators are outside. Okay? Now, because of this exercise, we can also deduce that that if P over Q is 1, then the graph is not bipartite. Why? Because if P over Q is equal to 1, then the Cayley graph of lambda over lambda 2Q, right? These are the graphs we really are interested in, is the Cayley graph of PSL to Q with respect to S. Then all the generators S are inside PSL to Q, and this is not bipartite. So how do you know that this is not bipartite? Because PSL2Q is a simple group. PSL2Q does not have a normal subgroup of index 2. And I just told you that if a graph of a group is bipartite, if a Cayley graph of a group is bipartite, it must have a subgroup of index 2, and it must take you the generator, like the general should take you from one side to another. Okay. So what's the nice thing about all this? That you start to see that all these little arithmetic, whether you are quadratic residue or not quadratic residue, plays a role here. Sometimes you are bipartite graph, sometimes you are not. Now I want to, the rest of the time, I want to spend, so let's denote XPQ, that's became like a standard notation for them. It's this Cayley graph of lambda over lambda 2Q with respect to this S, and we have to remember that it's sometimes the group PGL2, sometimes PSL2, depending whether P is quadratic residue mod Q or not. And now,
wait, is it enough?
What?
Is what you said is enough to state that it's not bipartite?
Yes.
There's another coloring?
Yes, because that's exactly what I said. Assume you have a Cayley graph, which is bipartite. Then I claim that it must come from, then the group must have a subgroup of index 2, which, and one side is the subgroup and the other side. Why? Take the side containing the identity, prove that this is a subgroup. Basically, the way to prove it is that all the words of length 2 are on that side, and that's, and this shows this is a subgroup. And then on the other end, PSL2Q don't have a subgroup of index 2. Okay. Now I still have enough time to show you maybe one of the nicest applications. Well, what I'm aiming to prove, and I want to finish this because this will come up later also in the high-dimensional case, that these graphs so first of all, we'll have large Girth. Theorem. The Girth of XPQ is at least 2 log Q. Maybe I will have to do minus some small constant, I'm not sure. 4 or 2, I don't remember, we'll see the proof. And in fact, we have even a better result, that if, that's always, that if P over Q is minus 1, if this is the bipartite case, then the Girth of XPQ is more than 4 times log Q. Now, why we care about the 4?
This is log
A log to the basis P. Now, this is already a dramatic theorem. Let me explain why. There is a story here. Yeah, now, the size of the group, XPQ, is approximately Q, right? Because this is the group PSL2 or PSL2 or PGL2, Q, and this is Q. And so this is approximately 2/3 log to the basis P. Now, P is this is a K regular graph where K equal P plus 1, you remember? It's log K minus 1 of N. X PQ is a K regular graph on N vertices. Because P is K minus 1. And this is 4/3 log K of N. And here is the story. Proposition, a trivial proposition. For every K regular graph on N vertices, everyone know what's the Girth? Did I say? The Girth of X is at most 2 log to the basis K minus 1. Now, what is Girth? Girth is the length of the shortest closed path in the graph. You go, and eventually you close it up, but not by going back. So it's like, if you want to be fancy, say that the closed geodesic which is not homotopic to the identity in the fundamental group. But it's simply, you don't have to be fancy, you just go. You have a loop, right? A closed loop, which is not obtained by going back and forth. This is called a loop. Now, why this proposition is true? This proposition is trivial. You start with a point. You start. Let's say that you have a graph whose Girth is G. What does it mean that the Girth is G? If the Girth is G, it means that if you start with some point and you go up, if you look at the ball around that point of radius G/2, then all the points there are different than each other. Because you don't see any loop inside. You don't see any loop, any closed path inside the ball of radius G/2. Which means that at radius G/2 it behaves like a tree. You think that this is a tree. Okay? Up to level G/2. So you count how many points you have here. So you have K point. You start with your point, you have K point, and then K minus 1, etc. You can see that in the ball of radius, G/2, the number of points is equal to 1 plus K times K minus 1 plus K times K minus 1 to the G/2 minus 1. This is the number of points in the ball of radius G/2, which is approximately K minus 1 to the G/2. So you deduce that N is greater or equal than K minus 1 to the G/2, and therefore, by taking logarithm, G is at most 2 log to the basis K minus 1. This is the proof of the proposition. This is just as simple like that. Now, Erdos proved by random methods that there exist fixed K, there exist graphs X and K, K regular, n going to infinity, such that the girth of x and k is something like 1 log to the basis k minus 1 of n. And so like half of the maximum possible. The maximum is 2.
If the issue was that they have a chromatic number also.
No, not yet chromatic number. Not yet at all. I won't have time today for chromatic. Just get, even this is a big surprise. Now you see what happened here. Usually the name, and then the people started like, Erdős did it using random methods. Now, if you have little experience with combinatorics, you know that usually people, you want to prove that something exists, usually the easiest way is to do it by random method. That's what we were taught by Erdős. Erdős invented all this random method. You prove existence by random. And then it's much more difficult to make explicit examples. And then various authors, from Goulis and others, made explicit examples, and they got numbers like, I don't know, 1.54, then 1.67 times log k minus 1. That's usually the game. You try to be as good as random, or as good as random. But here, suddenly, look at this case. We are getting better than random. 4/3. This was a big surprise. Because it's very rare that in combinatorics that you can win over random. This is one of these few cases that there are explicit constructions that are better than random. Now this was done almost 30 years ago. It's still a famous open problem. Where is the truth? 2 or 4/3? This is the absolute maximum. This is the best non-existence theorem by random, and nobody knows, neither by random nor by, like a year or 2 ago, there was kind of a sensation that 2 French people sent a paper, was even accepted for publication. They claimed that they imitated this quaternionic construction, and they went to octanions. That's for you, non-associative. This is kind of a not just non-commutative, but non-associative algebras, and they claim that they proved 12/7 log k over n, but there was a mistake in the paper which could not be repaired. So this is still an open problem. Many students of nonlinear try to either get the 2 down or the 4/3 up, and nobody knows where is the 2. I'm not sure if there is even a good guess what's the 2. Anyway, let me take, it's amazing that what we are doing is fairly fancy with Ramanujan, but the proof here is fairly simple. The proof here needs a little bit of computation. The proof for that is almost trivial. It's 1 line. So let me do the line of the first, which is 2/3. That's good enough, not good to overcome the random. Let me do it here, and maybe I don't know if I will decide if I do it at all or not. It's a bit computational, the other thing. But here, it's very simple, because you see, remember where we came from. What are our generators? Our generators, you remember, are these alpha 1 up to alpha s, alpha 1 bar, alpha s bar. And these are the p+1 generators. And they generate a free group, right? The Cayley graph of lambda with respect to s is a tree. p+1 tree. What does it mean? And they are free group. It means that if you take a path in this tree, it's never come. Okay, hold on. What does it mean? What is the girth of a Cayley graph? The girth of a Cayley graph, you take a path, the shortest closed path. In a Cayley graph, whatever happens at one point happens exactly at any other point, right? If you shift. So you can really assume that you started the identity, and you take a path. What is a path? A path is a word in the generators, right? You go to the immediate neighbor is by one generator. You go to the next one, you multiply by some other generators, etc. So it's really like going on, you take a word in the generators which close down back to the identity. It's a relation in the group if you want, right? It's equal to one. In the tree, there is no relation, because in a free group there is no relation, provided this is a reduced word. What does it mean, a reduced word? You are not allowed, after you multiply by alpha, you cannot multiply immediately by alpha to the minus 1, because that will take you backward. Okay? So, but this is for the free group. In the Cayley graph of lambda over lambda 2q with respect to S, what does it mean? When will you have a loop? A loop here really means that you have a word, a non-reduced word in alpha 1, alpha s, alpha 1 bar, alpha s. A non-reduced word, because that's what we want. We are not allowed a line to go backtracking. Non-reduced word, which is in lambda 2q. This is the meaning. Of course, in the finite graph, in the finite motion, we do have a closed. Always we have a closed path, right? The Girth, if you want, the Girth is at most log, twice log to the log of m, right? In a finite graph, k-regular graph, we always have closed loop, right? It's not a tree. K-regular graph. So the question is, when we are falling into this lambda q, so what we need? We need some w, but now remember, what are our elements? What is the norm? What is the quaternion norm of this element? All our elements are go back to the original definition. They are integral quaternions. What is the norm of a product of quaternion? We all know a norm of the product is product of the norm, right? So the norm, if w, so this is equal, I claim, to p to the L, if the length of w is equal L. If the length of w is equal L, then the norm of this product is exactly p to the L, because I just take a multiplication of element of norm p. The product of them will give me an element of norm p to the L. And I need, and now somebody tell me that this is inside lambda 2q. So this is an integral quaternion. So this w now is equal to a0 plus a1 times 2q times I. I'm writing it like that. Plus a2 times 2q times j plus a3 times 2q times I times k. I'm getting such a quaternion element if I multiply L quaternions of norm P, right? I claim now, and I will finish in 2 minutes, I claim that A1, A2, and A3, one of them is not 0. At least one of them is not 0. It's important for me, without A0. Why? Because if all of them are 0, what does it mean? It means that this word in the integral quaternion is equal to A0, to some scalar, right? But the scalar is in the center, which means that as an element of the group lambda, this is the trivial element, already without taking mod q. But we know that that's not the case, because this is a free group. There is no word in the generators, non-reduced word, which comes back to the identity in the group lambda. They can come back to the identity only mod q, but not really to the identity. So at least one of them, okay, this is since lambda is 3. And therefore, at least one of them is non-zero. And therefore, P to the L, so now compute the norm, P to the L is at least, now P to the L is equal to A0 square plus A1 square 4Q square plus A2 square 4Q square plus A3 square 4Q square, and simply P to the L therefore is more than Q squared.
Can't you claim 4Q?
What?
Can't you claim 4?
Yeah, I can claim 4.
It's only constant.
I can claim 4, but I don't care. I mean, it will give me a minus. I just said that here I could even add a small constant. So therefore, L is at least log to the basis P is 2 log P of Q. That's all. So trivial. So here is without Ramanujan. We don't need all the fancy stuff. Next time, so I tell you, I think what I probably will, I really want to manage to do at least some of this generalization to higher dimensional, because the course is about higher dimensional already this semester. So probably we'll talk with Ron, maybe we'll give a talk for an hour. We'll take a break after that for maybe 15 minutes, and then I'll give next week another half an hour, because I really want to finish with the Ramanujan graphs. So please keep in mind all this. And the last week, I will give you kind of introduction to Ramanujan complexes at least. This, and the second semester, Gil will start to talk about the higher dimensional combinatorics.